Good afternoon, everyone, and welcome to our fifth day of our student webinar series. I'm hosting today's session two, so if you've been attending these in the past, you're probably gotten a little bit familiar with me, and sorry we couldn't change it up a little bit here. I guess I was the only one available on a Friday afternoon. But anyhow, we're happy to have you here today, and we have a great session today. So we'll get started right away. So first of all, for those who don't know me, my name is Darius Fadanelli, and I will be moderating today's session. Quick background, I graduated in 1989 from University of Michigan, and I joined Altair shortly thereafter. And I've been with Altair ever since, so it's been 31 great years. And majority of the years, I managed our technical support operations for US, and also for a few years, I managed our technical support operations globally. Last about 4 years now, I've been managing our EDU outreach. And so my goal is to help students and faculty get access to our tools. Jumping into what to expect for today's, we're using GoToWebinar. And if you've joined before, you're familiar with it. But the first thing is some people have an audio issue when we switch speakers from me to the next speaker. And if that happens, please go to the audio tab here on the interface and then change it from computer to phone call. And that seems to resolve the issue for almost everybody. Just so you know, you are muted, and because we're recording this so people can watch it later on. And all these recordings will be made available usually within 24 hours, business hours. So this won't be available till Monday afternoon, and all the files that we, if there are any that we can share, will be also presented for you to take a look at. That will be on the same page that you use to register for these sessions. If you do have any questions, please post them in the question tab, whether it's about the Altair, our products, or the current session presentation, and we'll get to it. We do, the specialists are here to help answer these questions for us, so we'll be able to take care of them. Looking at today's agenda, we got a lot to cover. Even though it's just two sessions, these are more, advanced sessions doing external aerodynamics and finite element modeling with HyperWorks. So they're longer sessions than the previous ones that we've had. And
Darius?
Yes.
Sorry to interrupt, but if you're intending to show something, I'm not seeing your screen. I don't know if anyone else is.
Oh, thank you so much.
No problem.
Somehow it was on pause. So today's session.
There we go. Okay, yep. Now you're good.
Yeah. So today's session, our topics are virtual wind tunnel and modeling with HyperWorks. And so we're becoming a lot of material in a short span of time. So hang on to your seats. I'll tell you that right now. Well, one thing what I like to do before we get into the first session is just to make sure that I do see some new names from to today's session compared to some of the other sessions. And so I just want to let you, again, understand that with Altair, our licensing setup is that, there's a few different ways to get access to our licenses. We have a floating license, and with the floating license, you will have access to all our software. The unique thing about our licensing system is that we also enable what we call partner products. So they're third-party software tools. You can check out what we have available on our academic website. It'll indicate under students. If you go to student tab / partners, you'll see which partners are there. And there's about 18 other third-party software that could be made available to you and your university. And most of you probably already have our free student edition, but just want to make sure for those who haven't, here's where you would go get it. So you can get your own personal copy on your laptop, good for a year. You can renew it at any time, usually yearly. But what happens is, in mid-year, we come out with a new release. Right now we're 2021, and next February we'll probably be out with 2022. And so you just go back to request form, request a new license, because that will be updated for 2022, and you'll be fine. Or of course, you can get access to your campus if they're utilizing our software. Many schools do. And if you're on a team, you can access the license by requesting a sponsorship. The link's here. But if you go to our academics site under students, you'll see an option for sponsorship for teams. So every team that requests it will get access. You just need to fill out a very simple form, and you'll be all set to go. And just want to mention that when you do the sponsorship, you get as many licenses as you need. You're not limited to just one or two. If you have 5 people, you get 5. If you have 20, you want 20, that's fine with us, as long as you're utilizing the software. A little bit, as I mentioned with our licensing, it's set up that you have access to everything. So you have access to all our different tools, whether it's optimization, structural, thermal, control system, etc., data analytics. And that's why we're covering a lot of these topics during our student webinar series. So just to kind of, if you want to practice or get some files to play with, if you get the free student edition, you'll be able to get access to this, the product. Go to help, and you'll be able to get some files there. Of course, when you get if you get a sponsorship license, you'll be able to do the same thing. We have also ebooks you could download, which are free. Many different topics are covered there. We even have learning the aerodynamics with Ultra Fluid X. So you can, if you want a little bit more details, that'd be a great ebook to download and look at. And then, of course, you can get any files that we will share with this recording too. It's asked, why should simulation be used, and why simulation-driven design is so important. A lot of times people are used to using simulation starting from their CAD, and they'll give the CAD, start CAE, continue modifying the CAD, try to blend in whatever CE results they finally do get with their CAD, and sort of make a hybrid of that, and then have to kind of continue to reiterate from there. And that takes time. And it doesn't mean you're starting with the optimal starting point. If you use simulation at the beginning, you can get a more optimized design, a more optimal starting point. Make your CAD from that. Since it's already had CAE done as the base of it, you need to do less CAE, and you can be running more in parallel with CAD too, because also the tools can help you modify your CAD in it and just continue from there. So it helps shorten this whole design timeline, such that you can be able to meet your deadlines and be able to also do more and come up with more optimal design. We find many teams, when they use simulation as part of their process, they're able to be able to deliver their final designs in advance, and be able to then get into manufacturing those and have less issues of putting together the vehicles in a rush right before any event they're going to. As you've seen so far, we have a lot of solutions that can help with that. We're covering most of these during our session, so I won't dive into each one, but if you do have questions, please reach out during today, and we can try to answer about some of these simulation solutions we have. So our presentation for today is external aero, and we will be focusing on using our virtual wind tunnel. Virtual wind tunnel is an extremely easy tool that's tailored for external aerodynamics. It's really designed for that process flow in here. So you'll find it's a very user-friendly tool that you can define your problems and get to your solutions really quickly. A lot of automation and is put into this tool, so you can again help simplify the process, and at the end it'll export a customized report for you. I don't want to take too much of Matthias's thunder, so I'm going to stop there, and let's but there's but using with Virtual Wind Tunnel is our UltraFluid X, which is a solver, and it's a GPU based solver, so it's extremely fast, really performance. It's defined to deliver optimal performance to do huge models and get them overnight. Most of the models people don't need that, but if you're talking 100 million cells type model, it can do that overnight. So it's very accurate. It uses the lattice bowl method, so it's a great fit for using GPUs. Right, on to our presenter. We're lucky to have Matthias here. He will be presenting about using Virtual Wind Tunnel for your external aerodynamics. He has his ME degree from TU Munich. He's been a member of the Formula Racing team since, or he was 2018, 2019. He did an internship in 2020 at Porsche, doing some exact same things we're talking about here. And he's currently working on his bachelor thesis at Altair, simulation of a Formula student car with UltraFluid X. So a lot of great background, and we're lucky to have Matthias with us to do this presentation. So let me switch over to Matthias here.
Hi everyone, Matthias here. I'm now going to give you a demonstration on how to evaluate external aerodynamics with Virtual Wind Tunnel and UltraFluid X. We will go through the whole process of simulating the airflow around a Formula student car. So I will show you the pre-processing, the solving, and the post-processing. For pre-processing, we will use Virtual Wind Tunnel, where we will import the geometry, prepare the geometry, then specify some refinement levels, and also tell UltraFluid X which variables we want to export. Then we will upload the simulation to a cluster where UltraFluid X is installed, and we will start the simulation there. Then when the simulation is done, we will look at the results and prepare some plots and some section cuts. So let's get started in Virtual Wind Tunnel. Okay, so this is Virtual Wind Tunnel, and first let's load the Formula student car. For that, just click here on Open. Then I will select the egn18.stl file, which is the whole car, and open it. It's also possible to load every component on its own, but for that keep in mind that every component has to have the same origin, or otherwise the parts won't be aligned correctly. So now that the car is loaded, let's activate the model browser and also the property editor. As you can see, now there are two more windows. The upper one is the model browser, where you have an overview about over all the parts that the car has. And also later on, as we're adding some refinement levels and section cuts, these will also show up in the model browser. Below that is the property editor. If you select a part, you can see different properties of that part in the editor. We will also use that later when specifying the size of the wind tunnel, for example. But first, let's check if the car is loaded correctly and if it was set up correctly. For that, I click on the measure tool and then on any part, for example on the front wing, because I know its size. And here it says 1.27 meters, which is the correct size. If you exported the model with the wrong units, which has to be meters, you will see here that the car may not have the right size, so please keep that in mind. Okay, to exit a tool, because we're in the measure tool right now, just click on the right mouse button and click on the check mark, or just drag the mouse to the left. Okay. And because we need those volumes later, because they are control volumes for the voxel size, let's hide them for now. For that, you can select them in the model browser by holding down Shift, right click, and then hide selected. In Virtual Wind Tunnel, you usually go through the tools from left to right. So here we first loaded the model, we measured it, now we could move it if the parts were aligned wrong. We could also add some systems. These, for example, are useful to align wheels. Okay, next I will check the normals of the car. For UltraFluidX, we need every normal to point outwards, otherwise the flow won't know where the outside of the car is. So here you can see on the top left, every red surface is pointing outwards and every blue surface is pointing inwards. So you don't want to see any blue surfaces from the outside. So this car was set up correctly, and now there aren't any blue parts, but if they were, it would look something like this. And to switch the direction, just click on it. Sometimes it's also possible to see some parts that have mixed normals. For that you would see maybe a blue spot here. There you can click on Find Mixed, where it will identify the parts that have mixed normals, and then click on Unify All to unify the normals. Okay. It's also worth mentioning that for UltraFluidX you can have parts that intersect each other. For example, the driver is not stopping at this level, but goes through it. This is okay, but every component on its own needs to be watertight. So there can't be any holes in the car where the flow can go through. This is the reason that, for example, this part actually has a thickness to it. So if we look at the normals again, you can see that the underside of it is also red. This means that there's a surface that's pointing downwards, and also a surface that's pointing upwards. So this is not just one surface, but a volume. Okay, now after checking the car, let's set up the wind tunnel. For that, click on the Edit Tunnel icon. And now you can type in the dimensions. Either you use those little windows here in the viewport, or click on the wind tunnel icon here, and then we can type in the dimensions in the property editor. Usually it's recommended to have or to measure the dimensions of the wind tunnel in car length. So for example, it's recommended to have 5 car length in the in front of the car, then 10 car length behind the car, about 4 car length to the left and to the right, and about 6 car length in the C direction as height of the wind tunnel. In this case, we will use a length of 87.5 meters, a width of 30 meters, and a height of 23 meters. Now, to specify the location of the car exactly, let's move the wind tunnel a little bit. In that case, I will use a minimum x value of -30. We can now skip the x max value because we already specified the length of the tunnel, so this gets filled in automatically. Then we can leave the y min value at -15, and the c min value will be moved down to -0.233. So now, if we check the left side of the car by clicking on this cube, we can zoom in. and we can see that the car is really sitting on the ground. As you can see here, the wheel is overlapping a little bit with the ground, but this is really recommended because this way you can guarantee that there won't be any fluid voxels between the wheel and the ground. Also, it's more realistic because, of course, there's a surface patch on the wheel and it's not completely round in reality as well. Okay, so now we can also put in the inflow speed, either by setting it in the properties editor, or we can again click on this cube on the top left corner, and now we can see the wind tunnel, and then double click on 40 meters per second, type in 16.7 meters per second, which is the speed that we will run the simulation at. Okay, so now the wind tunnel is set up correctly, and we can continue by setting up the car parts. And if you lost the car in the viewport, you can simply select a part and then click on the magnifying glass, which will fit the selected. So now you have a centered view again. Okay, now let's tell Virtual Wind Tunnel what the different parts of the car are. For example, now it doesn't know which part are the wheels or heat exchangers, so we need to set it up. Let's start with the heat exchangers. For that, let's hide every part except for them. In the names, it's recommended to also include the group of the part at the beginning of the name. So, for example, as I did it here, you can see that many parts begin with body, and some of them begin with HX, which stands for heat exchanger. Also, there are some custom volumes, and also there are moving reference frames. So now let's select the heat exchangers, right click and isolate them. But this isn't all, we also need to include the frames. Okay, so these are both of the heat exchangers. To set them up, click on Identify Parts, where a new submenu will open up. And here you can now specify heat exchangers, wheels, fans, and body parts. By default, every part is loaded as a body part, so there's no need to set it up. But now we will set up the heat exchanger. So click on the symbol. And now, as you can see, there are different areas of the icon you can click at: the inlet, the frame, and the outlet. Also, the small window here shows different heat exchangers. So by double clicking on the name, we can change it. Let's change it to HX left. Click on the inlet symbol, and then select the inlet of the left heat exchanger in the 3D view. Now click on the frame, select the frame, click on out, and select the outlet. Now we can click on plus here, add another heat exchanger, call it HX right, select it, select the inlet, click on the inlet, select the frame, click on the frame, select the outlet, and click on the outlet. As you can see with the colors now, every part is set up correctly, so we can just exit the tool again. To make sure that we selected the right part for the right side, we can hover over the Identify Parts icon, and then this one shows up. Click on it, and now this shows you an overview of all the parts. If you right click on the top row, you can also show the groups, which is now where you can now see which heat exchanger a part belongs to. So for example, the left frame is part of heat exchanger left, the right frame is part of heat exchanger right. So we can check it here if we set it up correctly. Okay, so this is the right setup. So we can proceed by setting up the wheels. Actually, before doing that, there's one part left to do, which is specifying the properties of the heat exchangers. So let's select it, any part of the left heat exchanger, for example, and then go to the properties editor, where we can set the inertial resistance and the viscous resistance. I will use an inertial resistance of 190.8 and a viscous resistance of 786.26. Now these values get synced with all of the left heat exchangers, as you can see here. But now for the parts of the right heat exchanger, we need to specify them again. So 190.8 for the inertial resistance and 786.26 for the viscous resistance. Okay, so now the heat exchangers are set up correctly, and we can set up the wheels. Okay, for that we can select every part of the car again, except for the cost and volumes. We can show them to have an overview over the whole car. Okay. So for the wheels, again, you have to press on Identify Parts, and then you can select either creating a MRF wheel. MRF stands for Moving Reference Frame, or you can just create a wheel. In both cases, you have to start with creating a wheel, and if your wheel has spokes, like this one does, you need to set up a moving reference frame. But if its rotation is symmetric, there's no need to set up a moving reference frame. Okay, let's start by selecting the wheels. So go on Create Wheel, and just click on every wheel of the car. You don't need to restart the tool every time you select a wheel, you can just select them all at the same time. And as you select them, you can see that Virtual Wind Tunnel adds the axis of rotation into the center of the wheel, and it also shows the direction of rotation. Okay, now we can close this tool. And now let's set up the MRF wheel. For that, now as you can see in this little window, first you need to select a wheel, and then you can select an MRF. So let's select the front left wheel, click on MRF, and now select this volume. So this volume has the same position as the spokes of the wheel, but its rotation is symmetric. That means that Ultrafluid X will create a rotating geometry in this volume, and this will influence the flow. Now let's do the same again. Select the wheel and select the MRF. To skip to the next wheel, you can just press that triangle, which is the same as closing the tool and selecting it again. Okay, now the wheels are set up correctly. And now we could select it again in the model browser and specify the wheel runs per minute. Actually, you need to select a wheel for that and not the reference frame. Yeah, so now here you can see the wheels RPM, and Ultrafluid X has a function to automatically calculate it. If you go to File, Preferences, and Wheel Speed Calculation, here you can choose whether you want to calculate the wheel speed by using the radius or by using the distance between axle and floor. In this case, we want to use the radius. And you can see that it calculated the speed to 678 rounds per minute. Okay, so now the wheel setup is finished. Okay, next we will set up the volume mesh. Just for a little explanation, I prepared a screenshot. So here you can see a section cut through the front wing, and the lines you can see is the voxel mesh. So as you can see, it's consistent of cubes, which are aligned with the coordinate axis, and with every refinement level we are going to add, the cubes get cut in half. And not only do the dimensions get cut in half, also the time steps are doubled. So in the same time as the equations get solved for this cube, they get solved 2 times for the smaller cube. We will set up different volumes in which the voxels will be refined, and also we will set up offset refinements, which means that we can define a certain distance from the surface in which the refinement level will be higher. As you can see here, it's done around the surface of the front wing. Okay, but first we need to define the size of the co-assist voxel size, which means the voxels that are in the wind tunnel, for example at the edges. So let's show the wind tunnel again. Click on Mesh Controls, Far Field, and I'm choosing an element size for the biggest voxels of 0.192 meters. And the reason for that is because you can divide that number many times before you get too many decimal numbers. So even for the smaller voxel sizes, it will be like 3 millimeters instead of a very long number. Okay, next we can define some box offsets. So click on this, and then anywhere on the car, and now there will be a box created around the car. We won't specify the dimensions yet, so we can just click on the plus symbol until we have 5 boxes. Okay. So after creating the boxes, we can type in the dimensions. For example, for the first box, which will have refinement level 1, I will specify the length as 17.3 meters, a width of 8.5 meters, and then height of 4.783 meters. This zone extends, just as we did in the wind tunnel, can be set by typing the numbers in here, and keep in mind that you only need to set up the minimum numbers, because the maximum numbers are already given by the minimum numbers plus the length. So in this case, I'm going to type in minus 8.65 for y, minus 4.25, and for z, minus 0.233. All those refinement boxes need to have a z min of minus 0.233, because this is the level at which the wind tunnel ends, and you always want to have the refinement levels also include the first level above the floor. It's also possible to let them go through the floor, but yeah, you can just define it as the same as the floor height. Okay, so I'm using the names here, so body box 1 will have refinement level 1, 2 will have 2, 3 will have 3, and so on, so we can know later on which refinement level is on which box. And now I'm going to set the dimensions so that refinement level 1 will be the first to come after the wind tunnel, which has refinement level 0, which is this defined value. And refinement level 5 will be the nearest to the car. Okay, so now after setting up all the body boxes, it should look like this. So this is box number 1, box number 2, then this is refinement level number 3, 4, and 5. And as you can see, they're always a little bit further downstream than upstream, because of course you have some vortices that are forming here, and you also want them to be included in the higher refinement levels. So now let's hide all of them to have better visibility. And next we're going to set up some more refinement boxes, but this time only around some of the parts. This will be one for the front wing and the under tray, and then also another one for the rear wing. For that, you also go to mesh controls, but only click on the small icon at box. And now you can select a part that will be included in a refinement box, for example the front wing. So for this one we want to choose refinement level 6. So the size doesn't matter here, because we will change it later. And now also for the rear wing, you can also select many parts by holding down Control. Now both of those end plates will be included, but again this doesn't really matter because we will set up the dimensions manually. Again, for that I will define refinement level 6, because in the front wing, the under tray and the rear wing you will have the biggest pressure gradients, so you also want to have the highest resolution to make sure that the flow is simulated properly. Okay, now let's specify the dimensions, and also by double clicking on the name you can change the names. I will change this to part box 6 front wing, and because the numbers I want the numbers to represent the refinement levels, I will also call this part box 6 rear wing. Okay, for the front wing, which also should include the under tray, I will use a length of 3.2 meters, a width of 1.6 meters, and a height of 0.233 meters, with a minimum extent of minus 2.42, a minimum extent in y direction of minus 0.8, and in z direction of minus 0.233. Okay, and for the rear wing, the dimensions will be 1.2 times 1.6 times 0.9, beginning at an x value of minus 0.2, y value of minus 0.5, and z value of 1.2. 0.27. Okay, and sorry, there's an error. This should be just 1 meter. So 1 meter in width will result in y min of minus 0.5. Okay, so now it's symmetrical. And again, you can see here that the box is further downstream than upstream to show the vortices that are generated by the rear wing. Okay, so the last thing that's missing now for the refinement levels are these offset refinement levels. So again, let's hide those, and now click on offset. You can either choose to generate a body fit refinement zone around the whole car, or just an offset refinement around chosen parts, which we will do here. So now we can click on parts. First I will select parts that will be included in the finest refinement, which will be refinement level 7. And I will use this one for the flaps and the main plane of the front wing. Oops, sorry. So I misclicked, so you can see there are now 2 part offsets. We don't need that, so we can just delete one of them. And then click on the other one. You can see this triangle lights up. So if you double click on that, you can go back to the controls again. And now we can select all the missing parts. And I also want to select those little wings for the finest refinement as well. Okay. So to specify it, let's click here. First change the name to refinement level 7, so part offset 7. I want it to have refinement level 7, of course. And here you can choose the offset distance. So for example, a distance of 0.096 meters would result in a number of 8 layers. So the first 8 voxels closest to the surface of the wings will be refinement level 7. But for me this is too much. I just wanted to have refinement level 7 for 4 layers, which means 0.006 meters. So let's see if it calculated it again. So now you can see that there are 4 layers of elements of refinement level 7, which means elements of the size of 1.5 millimeters. This will result in a distance to the car of 0.006 meters, so 6 millimeters. We also want a refinement that's not too big, so we will add another offset refinement, which will be for parts that are not too critical. So let's click offset again and choose the wheels. Then those body parts. And also those A-arms. If you selected a part wrong, just hold down Shift and click on it again. Okay, so now that all the parts are selected, we can go ahead and type in the settings. So either you can now end the tool and type it in the property editor like we did before, or you can just specify it here. So this one will be refinement level 6 with a distance of 0.012 meters, which will result in 4 layers. Okay, so that's it. If we look at the results again, we can see that these are now the refinement level 7 voxels, Then there's the refinement zone that we specified around the front wing and the under tray. And then here's the first body box, or the fifth body box that we specified. So this is refinement level 4, 5, 6, and 7. Okay, now let's also rename this part offset to part offset 6, because it has refinement level 6. And then maybe you remember that we have hidden those custom refinement zones. And keep in mind that in case you want to hide those and not include them in the simulation, you have to delete them. If you just hide them like this, UltraFluidX will still see them, and because right now they're specified as body parts, it will also handle them like body parts. So the flow will go around these control volumes. So if you don't want to use them, delete them, but we're going to use them as custom refinement zones. So either by right-clicking on it and choosing custom zone, you can identify them as a custom zone, or if we go the same route that we just took, we can choose mesh controls and maybe first show them. Then choose mesh controls again, click on custom, and then click on those custom refinement levels. We want those ones to also have refinement level 6. Okay, and that's it. They're already named correctly, so they have the 6 in the name. So now we are finished with identifying the refinement zones. So let's hide them again for visibility. And because we chose part offsets, we also while hiding the offsets, we've hidden the parts themselves. So we can just choose them again by selecting everything and clicking on show. Okay, so now there are only a few details left. For example, we need to specify the material. You can either just use the material that is given by default, or you can define a new one where you can choose all the values yourself. For this simulation, we are just going to use the default values because they are pretty good. Then you also have the possibility to add a belt system, which is a belt system just like it is in wind tunnels. So one belt for every wheel and then a belt in the center. By clicking on the small icon, you can type in new dimensions, or you can deactivate some of them. For example, you could choose to deactivate the big one in the middle. And you also can exclude them from force calculation. This is mainly useful for comparison between a wind tunnel and a simulation. But because we just want to have the simulation and not compare it, we are not going to choose to use belts. So either we can delete them here, by clicking on them, right click and delete, or you can also just select them here in the model browser and delete them. Okay. Now under the output menu, you can select which values you want UltraFluidX to export. For example, you could define some probes. Again, these are useful for comparing values between the simulation and the wind tunnel, so we won't use them now. You can specify section cuts. You can choose surfaces that you want to export as their own, so for which you want to export the values on their own. And you also can create volumes. In this case, we just want to use some section cuts. To add a section cut, just click on the icon. And now you can choose different planes where you want to place them. So for example, let's put one to the XC plane, the YC plane, sorry. Now here we can set an output frequency in the start iteration. In this case, an output frequency of 500 will be enough. And as a start iteration, I will choose 10,000. This means that every 500 of step will be exported, but only starting at step number 10,000. We can check it here. For a simulation time of 5.1 seconds, we will have 16,000 steps, which means that there will approximately be 12 section cuts or 12 time steps for which the section cuts will be exported. So if we click on the section cut again, we can specify the location, and for this one I will choose an X value of -2.1. Then I will also generate a new one on the XC plane, again with the output frequency of 500 and a start iteration of 10,000. And as a location I will choose an X level of a Y value of -0.3. Then another one a little bit further outwards, so a Y value of -0.6. And just for this demonstration, let's just add another one. Usually I would add much more, but for this case I think it's enough, just to show you how it works. So one last one in the X and Y plane, again with the same output frequency, starting at 10,000. And as a C location I will choose -0.2. So this one will show the flow under the under tray. Okay. So let's export the simulation. For that, just click on the triangle icon at the run icon. So now here we can choose the name of the run, the number of GPUs we will use. In my case this will be 8. Here we could also change the inflow speed again, but we already did that. You can change the runtime. You could, for advanced users, use the time step scaling, which enables you to simulate a same time frame, like 5.1 seconds, with less time steps, so the simulation will be faster. And also you can choose the material again, but we will keep all those settings as they are. Of course, we will leave the moving ground activated, also the rotating wheels, and also the mesh preview. So let's export it. And now it wants us to change the names of all those section cuts and so on, which don't have an underscore, because you can't use spaces in the names, but it's easy just to click Auto Rename, and it will be renamed, automatically. Okay. So now one STL file will be exported, which includes the geometry of the car, and also an XML file, which contains all the settings that we just did here in Virtual Wind Tunnel. And I will show you now how the XML file looks like. Okay, so this is the folder in which we just exported the simulation. And as you can see here, there's an STL file for the geometry, and also an XML file with all the settings. So let's take a look at the XML file. Okay, so as you can see here, there's all the settings that we just did in Virtual Wind Tunnel, starting with the number of iterations. Here you could also change the Mach factor that I talked about previously to get fewer iterations for the same time frame. This is the name of the coupled STL file. And then, for example, here are some settings for the surrounding air, for the wind tunnel itself. Then starting here are all those refinement boxes. Here are the part offsets, naming every part that is included in the offset. Again, here some offsets for the wheels, or refinement zones for the custom refinement zones around the wheels. Here are the wheels itself with their center of rotation and their axis for the rotation. Also the revolutions per minute are included here. So as you can see here, there's everything that UltraFluidX needs to know combined with the STL file. And this XML file is really nice to just look at before starting the simulation to check if you have all the right settings. And also if you want to look at a simulation that you've done in the past, it's easier to just look at the XML file instead of opening the file again in Virtual Wind Tunnel. Especially because the XML file is always included where you started the simulation, so it's easier to find. Okay, so after checking this file, let's upload the XML file and the STL file to our cluster and then start the simulation. The upload is now complete, so let's start the simulation. First you have to activate all those UltraFluidX commands, so let's source it. And for that you need to know where your UltraFluidX is installed. In my case it's here. In the scripts. And then the file is called zufxenvironment.sh. Okay, now we can check it by testing out the help command. And here you can see everything that can be done with the UltraFluidX command. We're going to use this one, so mpi run -np, then specify the amount of GPUs we have. I'm using another cluster than the one that I was expecting, so I will have 6 GPUs. So I have to put the number 6 plus 1 here, so 7. Then UltraFluidX. Solver deck is our XML file that we exported. And then we also specify some options, for example, -o to specify the output path. Okay. So let's check the file where, let's check the location where I uploaded the files. Okay, so I uploaded the whole UFX simulation folder. And as you can see here, there's the STL file and the windtunnel.xml file, which is the solver input. Okay, now we have to export the GPUs. For that, you need to find out the IDs of the GPUs that you can use. In my case, this will be 227. Now we can start the UltraFluidX command. So -np7 because I use 6 GPUs. UltraFluidX. Then the solver file. -o output, which means that the output will be in a folder called output. And then I will use the greater S symbol and EGN18 -log.txt to save the log file to this location, and then also the AND symbol to let it run in the background. Okay, now let's check the log file. For that, we will tail the last 100 lines of this file. Okay, as you can see here, now he's beginning to start the simulation, and the first steps will be running or generating the volume mesh of the simulation. As you can see here, now it started meshing the custom zones, and I will get back to you as soon as the simulation starts with the first time steps. So this is what the log file looks like when the simulation was running for a while, and as you can see here, currently we're at time step 33, and here the estimated simulation time, or estimated remaining simulation time, is 35 hours. If you want to look at the estimated remaining simulation time, make sure you have the simulation running for a few time steps. I would say maybe at least 20 or 30, because at the beginning the estimation is quite rough, and then it converges to the right level. So now I will show you some section cuts in HyperWorks CFD. Before showing you the section cuts in HyperWorks CFD, I want to show you the folders. So after exporting the simulation from UltraFluidX, it looks like this. This is the outputs folder we specified. And then usually here are more than just this one folder, containing, for example, the surface data, full data, coefficients data, and so on. Because we only have time to look at the section cuts now, and because it's because of the download size, I just downloaded the section cuts to my computer. And also there always is this summary file, which includes the most important values. For example, here you can see the aerodynamic coefficients. So the drag coefficient is 1.1 and the lift coefficient is minus 1.86. Also you can see the flow rate through the porous medium, total runtime, and different details as well. Okay, so now let's look at the section cuts in HyperWorks CFD. For that we have to switch to post-processing. Then click on this icon to open a file. And these are the results of another simulation I've done of the same car that was set up the same way. So I have some more section cuts that I did. So let's, for example, look at the XC300 section cut. And to get all of these ranks, which are parts of a section cut, all at once, I will open the SOS file. So we can't see anything yet because we're in the top view, so let's change that. And by right-clicking on the fluid volume, as the section cut is called, we can change the color. And instead of choosing a constant color, we can also, for example, color it according to the time average pressure. Or we could also color it like the time average velocity. Here you have some more options. For example, you could show vectors or contour lines and so on. And also you can change the color map. For example, I like to use the rainbow color map. And because it's very useful sometimes to look at the coefficients, for example the total pressure coefficient, you also have the possibility to do that. For that you have to use the calculator, where you can add a variable and an expression for that. The expression has to be a Python expression, and As a quick way, you can also save those, which I have done. So I have set up the coefficients or the formulas for the coefficient, for the pressure coefficient and also the total pressure coefficient. Now that you have added them to the calculator, you can also use them for the section cuts. So instead of choosing the time average velocity, we can now also choose the total pressure coefficient. And this is a really good way to show the flow and to track the so-called clean air. And this way, it's a nice visual way to evaluate your aerodynamics. If you want to add another section cut, just go to File, Import, and then look for the other one, for example, the XY0 section cut, which then will be added. And this works the same way, so we can choose another color. And this way you can evaluate your aerodynamics. So I hope you liked this demonstration, and I hope you have fun testing these programs by yourself. Bye.
Thank you, Matthias. I really enjoyed that presentation, and I think you covered virtual wind tunnel with UltraFluidX quite well there. If anybody has any questions, Matthias is online here to answer your questions. So please use the question tab and let's see if Matthias can answer your questions. While you're doing that, we'll continue on because we have a lot to cover. So the next section we're going to be covering is related to both the finite element modeling and also being able to do a little bit of post-processing too. But so we're going to be talking about in the next presentation mostly about HyperMesh, which is one of the leaders in finite element preprocessor. So it allows you to manage your complex and simple models too. So it supports a wide variety of CAD and software interfaces, and basically we call it CAD and software neutral. So it makes it a great fit for no matter what type of solution or domain you want to work with, if you're using our tools for this, or you're using other third-party tools. So we allow you to basically work in this open environment, and we feel that it's allow you for rapid model generation, manipulation, and modifying. Over the last couple releases, we've done a lot of changes to HyperMesh's GUI to really allow it to even be more user-friendly and speed up the process in here. So whether you're doing laminate modeling, solid modeling, morphing, the tool really allows you to do that in a very convenient and obvious way. Without taking much more of Eric's thunder away, I won't say anything else about HyperMesh. If there's time, Eric will hopefully be able to show a little bit of Hyperview, but if not, we won't go into that. But Hyperview is the next step. And basically, it's a post-process. So once you set up your model, submit it to either our solver or some other solver, it allows you to be able to visualize that data and understand what's going on. It has an amazing amount of features and even automation in it, so you can really dive into what you're looking at and be able to automate some of these reportings that you might need. So again, I'm going to jump to our next presentation, and which is going to be done by Eric Larson. Eric Larson went to Michigan Tech University here and got his degree in mechanical engineering. He's over 30 years of experience, with almost about 15 of them here at Altair. I've had the privilege of working with him for most of those years, and he's works with me on our EDU program. and he's a great asset. The faculty and students love all his presentations and teaching he's done in a variety of different topics. And I'm going to switch over to Eric. Eric, let me make you presenter.
Excellent, thank you. Okay, so let me show this here, and hopefully my screen is showing.
Yes, sir, I can see it.
Excellent. Okay, so now we're going to be talking about hypermesh, and in regards to setting up an analysis, and this will kind of prepare you for the other seminars coming up. Next week we'll be talking about analysis and optimization, and there's some composite and analysis. And really, the core of doing these high level, or the beginning part of doing these high level types of analyses, is to use the hypermesh software. And what hypermesh is going to allow us to do is very easily bring in geometry, mesh it, prepare it for the analysis, create your properties, create your material definitions, and establish your loading and your constraints, and set that analysis up, or set that model up for analysis. One of the strengths behind hypermesh is the fact that it is a universal preprocessor. It's really blind to whatever software you're going to be running your analysis on. We can equally well and equally easily set up an analysis for any of the popular commercial solvers that are out there. What we're going to be talking about is a setup for our OptiStruct solver, but the steps that I go through, the processes I go through, are going to be very similar, with maybe some minor deviations for any solver that you want to set up. Now, what I'll do is I will run this through the entire process of bringing a model in, cleaning it up, meshing it, establishing the materials and the properties, setting up the loading conditions, and we'll run it and then take a look at the results in Hyperview. But before we do that, just to kind of a brief introduction to the interface of HyperMesh. And if you have ever used HyperMesh before, this is going to look fairly different from what you're used to. This is our next generation of interface. It's really been many years in the making, and is the future of what HyperMesh is going to be. It is a very modern interface. Has some incredibly easy to use tools that are very powerful and have taken the decades of experience that we've had with HyperMesh and brought it into the next generation. So to work within this, we have main portions of the screen. Of course, we have the ribbons up here, and they're going to be broken up into all of these different categories. So as you go through each one of these different categories, you're going to get a new set of icons. Many of these icons are multi-function icons. So some of them I'm just going to click on it. It's going to take me to the solid functionality, and maybe a blowout or a explode out version down here where I can go to different functionality. But some of the icons are going to actually have different functionality baked right into the actual icon. So if I come here, for instance, to stitch. If I come to here, it's stitch surface. If I come over here, it's suppress edges. If I come to our geometry creation, I can create combine extend, or do a combine extend lines, create polylines, circles, rectangles. So many of the icons themselves are going to have different functions right there in them. The main graphics window is where your part is going to live. The standard model manipulation within HyperMesh is to hold the middle mouse button down for a rotate. And you see wherever I click the middle mouse button to start that rotate, that's where it's going to put the center of rotation. So I just release the middle mouse button, come down here, hold down, and the center of rotation will become there. So it's very easy to manipulate that center of rotation. If I want to pan the model, I just hold the right mouse button down, and I can move the model around. And then zooming is going to be controlled with my my scroll wheel here. But we don't want to lock you into that, and this has been a big change for HyperMesh. If I come here to Preferences and come to Mouse Controls, I can actually change these to whatever I want them to be, and that's definitely a big change for HyperMesh. HyperMesh had always had hard-coded rotations, zooms. So now you can orient or change your mouse configurations to whatever you want them to be, make it a little more comfortable for you. The remaining portion of the screen that we talk about is over here, and this is the browser area. And it's really kind of the heart of all of the information about your model. This is going to handle the graphical information. This is going to handle all of the detailed information. If I come to my model browser here, I'm going to be able to see all of the different aspects that I have, or different things I have in my model. You can say I have 2,352 elements, 3 load collectors, 13 components. And if I double click on any of these, it's going to actually take me to the, well, it was already open already, so it didn't do that. It's going to take me to the little browser here where I can control those. So each different part in my model is going to be broken out into what we call a component. That's how we organize our models in HyperMesh. And if I click on any of them, I can get information about it, what the property is assigned to it, and none is assigned to it yet, what the material is. If I double click on elements, it's actually say that I've got too many of them to show a browser for, but I can select them there. If I come to load collectors and double click on that, I get the load collectors browser here, and so I can see the different load collectors that I have. If I come to the components, this is where I can now change the visualization of my model. So I can turn on or off all of the geometry or the elements for each one of my different parts in here. And I can control how my geometry or mesh is shown, whether I'm showing it in a wireframe or shaded, or the wireframe with the surface lines, or just pure shaded geometry. So I can control the visualization that way. Selecting things within HyperMesh this is a real big change from the previous version, and it's a real powerful way of dealing with selection. So if I come up here, this is what I'm selecting, and if I want to, right now it's just all. And if I click on something, it's going to go to components. So I'm selecting this component. If I want to pick elements, all I need to do is click. Let me deselect that. If I click E on my keyboard, you see it changes to elements, and now I can pick elements. And I pick them individually, or if I hold the control key down, I can pick them, add 2 selections, or I can even drag a window to select them, and it tells me how many I have. And then from there, if I click, say, the H key, H for hide, it will hide everything that's selected. You see it grabbed a few things behind there as well. And if I click the A key for all, it will bring everything back. Another neat function that we've added is if I come here and let me click C for component. So I'm going to click that component. If I want to now select all of the elements within that component, all I have to do is click E to switch to elements, and any element that's associated with the component that I just selected will be selected as well. And then I can manipulate them or change them or do whatever I want to them. Or if I want to just outright delete them, I just click the delete key and the elements will be deleted. We, of course, have undo functionality. So if I come up here to edit, undo, it's going to show all of the different things I had. Now, we can't just kind of cherry pick from this undo list here. I do have to sequentially undo things. So I could undo my deleted elements and now they're back. But if I come to something a little further down, the show components, you can see everything's highlighting to that. It will undo all the way back to that functionality. So selecting something down the list will grab everything that happened since then and undo that as well. But in the interest of time here, let's kind of now move on to how we're going to go about running an analysis. So I'm going to come here. I'm going to open up a model here. If I were to be starting from geometry, I would actually come here and I would open come to open, and I'd select geometry model. It would take me to here. I'm going to say don't save, and then I can pick the geometry model I have. And you can see we support all of the different popular geometry packages that are out there. And no matter what format your geometry file is in, you'll be able to very easily bring it into HyperMesh. The model I'm actually going to be working with is a HyperMesh model. And there's a reason why I'm doing this from a HyperMesh model and not from geometry, and that is I want to utilize this model to show you how to repair geometry problems. But HyperMesh is so good at repairing problems on its own, if I brought this in at geometry, it'd fix all the problems and I'd have nothing to show you. So just realize that all of the problems that I have with this model are there because we put them there. You will typically not see a model or any geometry come into HyperMesh that's as bad as this is. And the problems that we have with this model, you really can't see them right here. I've just got the one component, and I can turn on or off the geometry. I have no elements, so that won't change anything. I could come here and change the color of the component, whatever I want it to be. But the problems that I have with the geometry, I actually am going to come down here, and I'm going to come to my visualization. Right now it's on automatic, so if I go into a tool where it can affect topology, it will automatically switch to a topology mode. And then if I right-click to get out of here and swipe through that, it'll go back to the component mode. If I want it to stay in a visualization mode, I just click down here, and then I'll turn off automatic and come to topology, and now it will remain in a topological view. And I want to leave it that way just so I can kind of give you a tour of the model without having to be in a function. So the way that we deal with topology in HyperMesh, in the case of surfaces, is a green edge indicates that those surfaces are bonded together. They're connected together. And a red edge is actually telling me that there is a problem and those surfaces are not properly connected together. Some of them are so close that you can't even see. Some of them are a little bit further away, so you can kind of see a bit of a gap in there. So what we're going to want to do is we want to fix these problems. So to do that, I'm going to come here to my geometry, and I'm going to come to this stitch function. What stitch does is it fixes that connectivity between the surfaces. And that's important because properly connected surfaces will guarantee that I have properly connected mesh. So I can come here to stitch, and right now it gives me this click on edges or select surfaces to stitch. You'll also notice on many, if not most, of our functions within HyperMesh, we get this little show picture. If I click that, what it's actually going to do is it's going to bring up a picture here, and it's going to show me a little video on how to perform this function. So as you're learning this for the first time, all you have to do is click on that little video, and there's no audio, and any words that need to be said are going to be in a little closed captioning there on the bottom. But it's going to give you a video tour of how to utilize that function and all the different things that you can do with it. And if I click these little down arrows, it's going to say click edges to auto stitch, so it gives me some help there as well. So the first thing I'm going to do is kind of auto stitch this, and I'm just going to do a window select, grab all of the surfaces that are in there, and click stitch. And you'll see that most of the red lines have been fixed. They've been stitched together. A few of them have not, and that can be controlled here with the maximum stitching distance. So on any function that's within HyperMesh, if you click these three little lines, learned within the past year or so that this is called a hamburger. Never knew that before, but anytime you see these three little lines, if you hear somebody say click the hamburger, that's what they're talking about. But this right here is referring to the maximum distance that I want those edges to connect. That, well, HyperMesh and FEA software in general is unitless. The units, the dimensions, the values that we are in are whatever your model was created in. So if your model was created in millimeters, this would refer to 1 e to the negative 3 millimeters. If it was inches, the same thing for inches. And you see, because of that tolerance, it fixed most things, but some of them were not. Another really cool feature with this stitch is now for the things that weren't, all I have to do is click on this one that I want to move, drag it up to the other edge, and it brings them together like that and stitches them together. So I'll come over to this one here. And the reason why I'm now doing these manually and not relying on the auto function is because the auto function, I can't guarantee which surface goes to which. And in this case, I want that one to come up to there. I don't want the top one to bow down, or I'd end up with kind of like a little dent in my model. So these I like to just fix manually, and I take and drag this over here, and now you see that all of my problems have been fixed here. In this case right here, it looks like I have a little extra piece right there, so I'm just going to right-click to get out of here. I don't want to see that again. And if I click Ask for Surfaces, I can now click that little surface, click, and that goes away. If I come over here to Surfaces, now this, I can't extend this down. I can't stitch them because doing so, you see it kind of messes things up. So I actually need to put a surface in there. So I'm going to come here to my Surfaces, and I'm going to click Patch, click this, this, and patch it, and it fills that surface in right there, and now I've got my my volume fully fixed here. And take a quick look around, and I can see that that everything looks good. I can also come here and oops. Now that I've fixed my topology, I can go back to automatic, or I can go to component, and we'll just leave it in component. I'll switch it back to automatic. So everything has been fixed with that. Now my geometry is ready to analyze, or is ready to move on to the next step. And whether you're going to want to do 2D meshing or 3D meshing, now is kind of the time that you would decide that. Looking at this model, it's obvious that this would absolutely be a 2D mesh. It's thin shell. It's it's a constant thickness. But I do want to quickly show you how to do a 3D mesh. Doing a 3D hexamesh with cubes and pi wedges, a little bit beyond the scope of the time frame we have here. So what I'm going to do instead is just talk about tetrameshing. Solid map is what we'd use, and we have some excellent tutorials and videos talking about how to do that. But tetrameshing I can do automatically, so I just come here to my tetrameshing. It's asking me to select the component, so if I pick the component or if I do a window select, I can come here, and it's now not allowing me to do that because I don't have solids. Fortunately, with tetramesh, I can come here to surfaces and pick that, and it will automatically select it. I could, when it comes to tetrameshing, as long as my surfaces are fully bound, I don't have any holes in them, I can do that. Otherwise, it's very easy to create this into a solid. Let me exit out of here. Oops. Oh boy. Oh, it went and meshed. That's why it was taking so long. If I come back here to geometry, I could come to solids. You see I have this bounding. I pick that, it will automatically select them all and create, and now this is solid geometry. So you can see going from surfaces to solids is very simple. But let me come back here to mesh, tetrahedral, select my surfaces. I give it a mesh size. 1 is probably good. And then I'll just click mesh, and what it will do now, it'll take just a minute here. We can see down at the bottom, it keeps flashing things, just letting us know it's continually working. And then it will create my elements, and these are now my tetrahedral elements, and I could go and mesh with them. And you can see it's a very, very nice looking mesh. It is a relatively small mesh because of that thickness, again, which is why we'd probably be leaning towards doing a shell mesh, which is what we're going to do. But if you've got something that you would rather do, or that would need a solid mesh, tetrahedral elements are the way to go in that regard. So let me exit out of here, and I'm going to undo my tetra mesh. Because the way that we're going to want to go with this now is coming back to geometry. I'm going to come to mid-surface. When I create my 2D elements, they are going to want to be at the middle of the part. So if I come to mid-surface, all I have to do is click Automatic. I pick my surfaces. I'm going to window select those. It's selected all 172. If I click mid-surface, what it will now do is it will create a brand new component, which I can see now here is this middle surface component. It lies perfectly between the faces of the other two. And now I can actually turn off my original component because I'm going to work strictly with this one. Now what I'm going to do with this geometry is I'm actually going to come here to defeature. And I'm going to remove some of the features within this geometry. So I want to come here, I'm going to come to fillets. And if I click find, oops, let me see what we've got. So minimum 5, that's probably a little bit outside of the range of this part. So let me come here to 1 and 15 and find. So it finds all of these fillets. I can add or remove from them, but if I click remove, now you see it's kind of straightened up my part. I'm doing this just to get a better quality mesh. If I were really doing a fine analysis of this, I would probably leave the fillets in there, but want to demonstrate the defeaturing. Holes are another thing that I can get rid of. So minimum 0, maximum 10. If I click find, you see it finds these holes here. And if I were to click remove all, it would make them all go away. This one's a little bit large to remove. So all I'm going to do is hold my shift key down, click that, you see it deselects that, and I click remove, and now it gets rid of all of the rest of them. Or I could have clicked them manually. So with the part now defeatured, I now want to come here to my mesh. So you see we have mesh and we have elements up here. Mesh is what we're going to use to create the mesh. Elements are what the tool that we're going to use to manipulate any elements that mesh that we have on there. So I'm going to come to mesh. Instead of tetra, now what I'm going to do is come to general 2D mesh here. It's asking for create. You see it automatically defaulted to selecting surfaces. So I'm going to grab all of those surfaces right there, and now it's asking me for a mesh size. So I'll say 5. And if I click mesh, it shows me my part here, and it's going to show me my quality on the part. And the elements are relatively good. It is saying that we got a time step issue here, and that's only if you were planning on running a explicit analysis on this. So we don't need to worry about that. But you'll notice here that this is a relatively large mesh. And if I come here to the QI range, you can see I do have a few problem elements here that I would want to fix, but really a lot of that is driven by the mesh size. So let me come back here, and I'm going to select my elements again, and I'm going to say instead we'll go to a 2-element mesh size. And that looks a lot nicer now. I could probably even drop that down a little more. There's not a lot of elements on this part, so I could probably drop that down a little bit more. So I come here, grab this again, and I'll say 1, and mesh that. And that's a really good mesh here. And you can see if I come here to QI, I've got no issues with the quality of my mesh, no problems with it. The criteria is good. It's overall, it's a very good quality mesh there. So with the mesh now complete, right-click to get out of here, pass through that. Now I have my elements. I've got my geometry, and again, I can turn on or off my elements, turn on or off my geometry, change the color of my my component there. Maybe I'll want to change it from the name middle surface. It automatically named it middle surface here, so I just click rename, and we'll just call it bracket. Telling me the number of elements, and now it's giving me some other information here about properties and materials. So I've physically described my part through the use of elements, but really now I have to define the analytical properties of my part. And that's where we're going to get into materials and properties. So if I come back to my model browser here, you can see it's showing one material ungrouped. Don't know what that is, but what I want to do is right-click in here and click Create a Material, because I need a material to define the behavior of this. So I'll give it a name. I'll just call it steel. Pick the type of material I'm going to create. A Mat1 in OptiStruct is a isotropic, homogeneous, linear elastic material. So all we need to define is the Young's modulus. So 210,000. 210,000 what? In this case, it's megapascals. I really don't have the time to get into the real in-depth discussion about unit consistency within a software. But when I'm working with a model, I have to define three things: a unit of length, a unit of time, and a unit of force. And that the unit of length is decided upon during the CAD process. In this case, it's going to be millimeters. I am going to use millimeters. I'm going to use newtons, and I'm going to use seconds. So in this case now, if I'm using millimeters and newtons, my pressure would be in terms of Newton per square millimeter, not Newton per square meter. So I can't use Pascal. I have to use a megapascal. So 210,000 megapascals. I knew my Poisson's ratio, and you see if I hold over these, it will tell me what each one of these is. Poisson's ratio, of course, is unitless. It's just a ratio, and 0.3 is fine. And my rho, my mass density, 7.85 e to the negative 9. Again, an incredibly small number. And the reason for that number is because the density is going to be in terms of megagrams per cubic millimeter. And all of that, it derives itself from the unit choice, from the millimeters, newtons, and seconds. If you are really having difficulty wrapping your head around unit consistency, if you Google the term unit consistency, there are some excellent papers out there and excellent charts describing unit consistency and even giving you samples of the popular unit schemes and some numbers in them that will help you out. Oop, I lost my row there. Okay, so now I've got my material defined. And the reason why I'm defining my material first, let me close that, is because now if I come here and right-click, I'm going to create a property. Properties and materials sometimes people kind of use them interchangeably. What a property does is it actually tells the solver the analytical features of the element. It's going to tell the solver what the type of element is. Many properties have information about the number of integration points, the style of the element. It defaults to P shell because that's the most widely used, and that's actually what I'm going to use. A P shell is a property shell, so a zero thickness, a zero physical thickness. The thickness is going to be defined mathematically here. If I were doing this with my tetrahedral elements that I showed earlier, I would make it a P solid. And then you see if I go to P solid, the T is gone. There's no thickness for a P solid because it has a physical thickness. And I'm going to do P shell. And now it's asking me for the thickness on the part. So what I'm going to do is I'm actually going to come back here and close this. It has saved my property. My property P shell is right there, because I'm going to come back to my component and I'm going to turn my original part on right here, and I'm going to zoom in here, and I'm going to come to measure. And what I want to do is I want to measure a distance. So I'm going to measure from this point to that point right there, and you can see it says it's 0.9 or 0.91 millimeters. So just a shade under a millimeter. So with that measurement, now I know that I can come back here to my property, and let me, oh, you know what? Let me double click on properties, because that will open up my property browser here. Come back here to property. Now I can come in here to my T, and I can type in 0.91. And now the last thing that it's asking me for is a material. That's the reason why I created my material first. So I come here and I pick my material that I want. I want that to be steel. I click OK, and now my property is defined. And to assign that to my part here, I'm going to come back here to components. I'm going to turn that back off. If I come to bracket, my component with my elements in it, and select my property, and assign that property to it, now every element that's within that component will be assigned that P shell of 0.91 millimeter thickness property and the steel material. And so now my parts have been physically defined. So my part has been described. It has been physically created with the geometry, and I've discretized that by creating my mesh. I've defined the analytical properties of that mesh through a property and a material. And now I need to define the elements or the features of the actual analysis, and that's going to be my constraints and my loads. And so to do that, I'm going to come back here to my model. I'm going to right click in here, and I'm going to create a load collector. So just like my elements are in a component, my loads have to go into a load collector. And I'm actually going to create two of them. I'm going to create one for my constraints and one for my my loads. And I need to make sure that those are in separate component or load collectors, because you'll see that when we get to the stage where we define a load step, we're going to reference each of them individually. So let me come here. And I will create a load collector, and I will call it loads. I'm going to call it forces. I'm going to make it blue because I like my forces to be blue. And close that. And then I'm going to come here and come and select that again and create another load collector. And this load collector, I'm going to make, oops, let me put that again. I'm going to make it red because I like my constraints to be red. And then I'm going to come up to here and call this constraints. Perfect. Okay. Now I've got my load collectors here. And if I double click on that, you can see my load collectors. I did create them in a specific order. I created my loads first and my constraints second. And the only reason that I did that, or the reason why I did it in that particular order, is because whatever the last one you create is going to be what we refer to as the current load collector. And that means that whatever I create is going to go into that current load collector. I want to create my constraints first. So with my constraints as the current, you can see it's current because it's in bold. So now I'm going to come here to analyze. My constraints are under BC's boundary conditions. And I want constraints. Now, like I said, this is a huge change to our interface. We've done some incredible things to it. We're continuing to evolve this interface. We're continuing to add features to it. It will at sometimes refer you back down here to kind of the old interface because we haven't created a we call them window that comes out from there. So what it's doing is you're just asking for nodes. So I'm going to come to here, and I'm going to pick all of the nodes. What I'm going to do is I'm going to pick a node on that surface, come here, and I'm going to say by face. And so it's going to grab all the nodes that are on that face. And then I'll pick this node right here and say nodes on that face as well. So those are the nodes that I'm going to have as my constraints. I'm going to hold all the degrees of freedom. Click create, and now I get my my little constraints there, and I can turn those on or off as I see fit, and return from there. So now I'm going to right-click on my loads. I'm going to make this my current by clicking Make Current, so that now when I create my constraint or my loads, they will go into there, and I'm going to come here to Forces, and I'm going to pick that node there. I'm going to say by path. And then I'm going to pick nodes coming around here. And all the nodes around that. I'm going to say that I want these in the Y axis. So you see here, Y is kind of pointing down. And I will make them, I will say -10. And click create, and you see now I get my forces acting down on that. So my part's been defined. I've got my constraints. I have my forces. The last thing I need to do is create what we refer to as a load step. So I'm going to right-click here. I'm going to create a load step. Load step is an instruction to the solver as to what I want run. So the analysis type in this case is going to be a linear static analysis. And this is why I had my constraints on my loads in different load collectors, because I need to refer to my constraints here. I'm going to pick my constraints for my SPCs. SPC is short for single point constraint. Pick my load. And everything is set. It's all ready to run. I click close, and now I've got my load case. So the last thing I'm going to do is come here to File. I'm going to save as a hypermesh model. I'm going to come to my desktop, put it in this webinar folder. Topology repair is fine. I'll save that. And now all I need to do is run this. So I'm going to come here to Analyze. You see it's defaults to the folder where it was saved last. And I click OptiStruct, and it will run that analysis. It's going to pop up the run window here. If everything went well, if I didn't mess anything up, it should get an analysis complete. So that looks good. Click Results. That will open up my results in Hyper-View, so we can visualize the results of this. This is supposed to. Okay, well, it doesn't seem to be. So what I'm going to actually do here is if I come up here to the top, I can click Set Page Layout. I'm going to split my window here. And if I come to this window here, I'm going to set this as a Hyper-View window. It actually defaulted to Hyper-View, so that works perfectly fine. And now I'll come here and open my results. So come here to Results. Oh, here we go. File, Open, Model. Come here to Model. I'm going to come to Desktop, to my webinar folder. I'm looking for this H3D file. Click Apply. And there's my results right there. I can visualize them. If I come here to results, we're going to change, see element stresses, and we'll show the von Mises stress and apply. Oops, I did it wrong. I'll try that again. Oops, element stresses, von Mises, mid. Doesn't like that. Let's try that again. Hold on just a second. Let's go the old way. Contour. There we go. And apply. There we go. There's my von Mises stresses. And I can average them so I get a little bit smoother. And we can see the results there. So relatively high load for a relatively thin part. So we're getting pretty excessive stresses there, pretty excessive deformation. But at least it gives you the idea of what you're going to do. So with the remaining 5 minutes, I'd be happy to address any questions that anybody might have. Please feel free to pop them in the chat, and we'll answer anything that you have. If there are no questions, or if you don't have a question, I appreciate your time. Hopefully you learned something out of or got something out of these presentations. Do keep looking at all of the different webinars that we've got coming up. Some really interesting, really useful ones coming up. My next webinar will be next Thursday, where we're going to take what we've learned here with the analysis and expand that into how to do optimization. But other than that, I'd be happy to address any questions that anybody might have.
Thank you, Eric. Fantastic job covering so much material in that length of time there. I know the new interfacer actually helps be able to show more in a shorter period of time too.
Yes.
I know some absolutely. Of the new students won't appreciate that as much as some of the old timers. But again, there's also, I want to reiterate that there's a lot of material. If you go to File and Help, you can there's additional tutorials besides how Eric showed that you can get access to videos. We try to make sure that if anything, you have over amount of materials that you can learn the tool. Also, we do have, as we've mentioned, some of our past webinars is the community forum. So students, you can go to our academic site and go to the community forum and search the database, post questions, and so forth. Now, if you're part of a team, you can actually email directly to our support staff, and they'll be able to take care of you. Of course, if you're on a team, you should indicate what team you're on so they can confirm that in the database and make sure they're helping out a sponsored team. All right, I see no questions. A little surprising here. I think a lot of people just need to dive into the tool and use it a little bit more if they haven't already. And we'll probably get some future questions. You can always come back to your next session, Eric, and ping you there. But yeah, this is kind of a two-part series because here going to optimization and so forth. It's kind of the next thing people usually like to do. I don't want to take up anybody's more valuable time, especially on a Friday late afternoon. We appreciate everybody attending today, and we hope you have a wonderful weekend and look forward to seeing you and others next week. Take care, everybody, and thank you so much, Eric.